and dear participants. We are at the 12th session of this faculty development program sponsored by AICTE Training and Learning Academy, AICTE New Delhi, online faculty development program on photonics, active learning in photonics, and active learning in optics and photonics. Today we have a very renowned resource person, Dr. Souad Lahmar ma'am, to present her talk on teaching optics in an active learning way. Before we start the session, I request my colleague, Professor Swapnil Undalkar sir, to introduce Dr. Lahmar ma'am. Please, Undalkar sir.
Thank you, sir. It is my great pleasure to introduce one of the international resource person. Currently, she is working as a professor at Institut Préparatoire Etudes, Scientifiques Techniques, Tunisia. She has completed her PhD in quantum chemistry at University of Paris, France. Soon after, she was assistant professor at the Faculty of Science of Tunis and a researcher at Laboratory of Atomic and Molecular Spectroscopy and Application. Also, she completed her doctorate in the field of theoretical chemistry, molecular spectroscopy, and pollution. After that, she was associate professor at Faculty of Science, Desert. She knows Arabic, French, English, Italian languages, out of which Arabic is her mother language. Madam has started her career in the year 1978 as a teacher at a secondary school. Her interested teaching fields are electromagnetism, quantum mechanics, atomic physics, optics, and laser. She was co-responsible for physics teaching at IPST, also co-responsible of exams at national level for recruitment. She is a coordinator and guide of different research projects for PhD and postdoctoral students. She is a referee at various scientific journals, invited speaker at local and international scientific events like workshops, conferences, programs. She is a founder member of Tunisian Society of Optics. She is a renowned resource person at UNESCO International Program in Physics and UNESCO project, active learning in optics and photonics, training of physics trainers, and also she is a coordinator of ALOV project in Africa. One thing I could say, teaching is the act of sharing knowledge we have been given others with hope that somebody in some way it again will be passed on. Thank you for giving me opportunity to introduce Professor Souad Lahmar madam. Now I request Souad Lahmar madam to start her presentation.
Thank you for this presentation. Thank you so much. I am very happy to participate to this workshop. I will start my presentation now. So you see my PowerPoint?
Yes, ma'am.
Yes, okay. I start by thanks, okay? Excuse me.
Yes, ma'am. Wonderful.
Slide, okay. So the title of my presentation is Teaching Optics in Active Learning Way. The title says optics, but it could be teaching physics in active learning way. Let me first show you where is Tunisia. I come from Tunisia. It's a very small country in North Africa. It has not a lot of, it doesn't have a lot of inhabitants, 12 inhabitants. It's a Muslim country. As Dr. Swapil said, our mother tongue is Arabic, and then second language is French, and English is third language. So please Excuse my bad English. It's my third language, and I will do my best. My first question is, why active learning? My first experience with active learning was on 2006. 2006 was the first ALOP workshop in Tunisia. It was the second ALOP workshop in general, and it was the first ALOP workshop in Tunisia. I attended this workshop as a participant. You can see the picture here. I am there as participant in the workshop. And since that date, I was really impressed by this, the active learning way of teaching. I used to teach in passive way until I discovered this, until I attended this workshop. So immediately on 2006, we decided to, with the other colleagues who has attended the workshop, to make a team and duplicate all the ALOP lab experiments and translate the manual in French. This is the first page of the French manual. Why did the translation was done with the Moroccan team. The Moroccan team has also attended the workshop in Tunisia on 2006. Why did you translate in French? Because in North Africa, science, in North Africa, I mean Tunisia, Morocco, Algeria, science is taught in French. And you can see here, maybe not, but the names of of both Tunisian and Moroccan group members. In the session number 1, David Sokolov, Professor David Sokolov, told you a lot of active learning and about the manual and so on. So I will come back very quickly later on the main to talk about what is active learning. But first, I would like to tell you that my first experience as a facilitator in ALOP workshop was on 2007 in Morocco. In this ALOP workshop, at the beginning I went there as a participant to check, because as I told you, we duplicated the material, we translated started translating the manual, and I wanted to participate once again to an ALOP workshop to make sure that everything is clear for me. And during this workshop in 2007, the original ALOP team facilitators asked me to present part of module 5 and 6, that is on optical communication. So I was very happy to participate, and it was with Alex Mazzolini, and it was a wonderful experience for me. And since that date, I was asked to become part of the ALOP team, international team. And since that date, we did a lot of workshops in Tunisia with our Tunisian team was leading these local workshops, and also I participated to international workshops with the UNESCO ALOP team. Do you hear me? Excuse me, do you hear me?
Yes, madam.
Okay. Can I continue?
Madam, continue.
Okay. So, From all the workshops I attended till now, it appears that the main physics teaching problems come from from a passive method. Why I say main physics teaching problems? Because there are many other problems. This is not the only problem, of course. And because of teaching problems, the number of students in physics and chemistry is decreasing drastically in Tunisia and I think all over the world. Excuse me. Let me first, please, I take these slides from David's presentation, just to remind those of you who has not attended the first session, what are the main problems of passive learning teaching method. In passive learning, the instructor, the professor is the authority in the classroom. In active learning process teaching, the instructor is only there to guide the students. In passive learning, the students are never asked about their beliefs before attending the course. They are often not allowed to discuss with the teacher or with the authority. However, in the active learning environments, the learning cycle is different. I mean, as David showed you, and we will see something like this today also, we ask the students or participants to the workshop, if it is a workshop for trainers, about any physics optics subject, for example, I don't know, let's say diffraction or interference, to make their prediction about one experience. And then after doing prediction, they make observation, they make the experience. So first prediction and then observation, that they make the experience in the lab, and they make comparison between prediction and observation, and they can correct. I mean, what we call prediction is what the students have in their mind before doing the experiment. It might be correct, it might be wrong. So if it is correct, it will be confirmed by doing the experiment. If it is wrong, they will correct their beliefs. So students' beliefs are challenged in this step. And then we allow participants or students to discuss together in the active learning process, which is not allowed in the passive learning way. Also in passive learning, sometimes the teacher do experimental experiences to show experimental results, but in general, the course is done in a classroom without any material, and the experimental results are presented as facts in the lecture. Whereas in the active learning way, they can do the experiment, see what happens in real time. In passive learning teaching, the experiment, if there is done after the course. But in active learning way, it is a very important part of the learning process. It is used to learn basic concepts even before doing a course. In our developing countries, North Africa and many other developing countries, the problem, there are other problems. I mean, teaching method is not the only problem. There is problem of lack of material, of equipment, of experiments. David told you in the first session that we can do, if we don't have equipment, we can do interactive lecture demonstration. It's better than nothing. I mean, the teacher is in the classroom and he shows the students the experiment, and they do the active learning process. I mean, observation, prediction, observation, discussion, and also the number of students in the classrooms, and ILD also is a good method for if you have a big number of students, you can make demonstration for them. It's better than not doing experiment. And another very important thing is that in this active learning UNESCO ILOP workshops, we use very basic material, very cheap. I mean, everything is almost, I will not say everything, but almost all the material used in those workshops is homemade, and anybody can do it, can duplicate it at home. So the main goal of the UNESCO Active Learning in Optics and Photonics workshop is active learning. I mean, when we do those workshops for trainers, the main goal is showing the teachers what is active learning. We are not there to teach physics. And the optics for these workshops is only a suitable because of the material, which is not very heavy to carry and very easy to duplicate, just to show what is active learning. Very quickly, here are the titles of the 6 modules of ALOP workshops. So David talked to you about this in the first session, but just a very quick reminder because I will need it later. The first module is about geometrical optics. The second is lenses and optics. It is also geometrical optics. The third module is about interference and diffraction, and now we come to the wave model. Atmospheric optics, it could be both wave and geometrical optics. And then the 2 last modules are about optical data transmission and wavelength division multiplexing. And what I am going to talk to you about today has a lot to do with this module, but we need all these also material or preliminary consideration to understand this problem. This morning, I saw that the first part of one of the presentation was talking in the first slides about optical data transmission. What I'm going to present today is I will also talk about optical data transmission, but it will be in a very simple way that students in secondary school would understand. You have here the link for the manual of ALOP and many other information. Thanks, David, for giving me this. Do you still hear me, please? Hello?
Yes.
You still hear me?
Yes.
I think they have a problem with my computer. Maybe I will have to.
You are audible, ma'am.
I think it's a problem from my computer. I can't do anything. It's blocked completely. Sorry, may I ask you a few minutes to restart it? Sorry, so sorry.
Yes, ma'am. Yes,
Can I do it?
Okay,
I'm
ma'am.
sorry. I'm sorry. I will restart my computer.
Okay, ma'am. Please restart.
Thank you. Thank you.
Madam will join within a couple of minutes, and we'll continue the session. Please.
Hello. Can you hear me now? Hello.
I hear you. Yes.
You can hear me?
Yes.
Okay. Hi, David. So I am really so sorry. I can't open the last version of my PowerPoint. So I will do my best with the old one, okay? I don't know what happened with the other version. So can I use an old one, and I will do my best with the old one, okay?
Yes, ma'am.
Sorry,
Yes,
so sorry.
Please.
Okay, let's go to, this is not a very good version, but we can do. Excuse me. Okay, we were there, right?
Yes, ma'am.
Okay.
But your screen is not visible yet.
Sorry?
Screen is not visible, ma'am.
You need to share your screen.
Can you hear it now? Can you see?
Yes.
Okay.
Yes, ma'am. Yes, ma'am. It's perfectly right.
Okay. Sorry. Once again, this is not the final version. It's an intermediate version, which is not complete, but we will do it. Okay. I can't come back to the previous one. Sorry. You hear me?
Yes, ma'am. Yes, ma'am.
Okay. So as I told you, the presentation has something to do with the optical data transmission. On 2017, a group of secondary school Tunisian teachers who have attended previous ALOPs, asked me to help them to present a project in Olympiad of experimental physics for secondary school students. And they suggested the project whose title was this in French, Lumière et photonique au service du son. that is light messenger. If I will translate this in English, I would say light messenger, as a messenger for sound. Okay, this is the group of the students. These are this three, and this girl are students. Here are the two teachers, and those are technicians with other persons, and I am there. Okay, I was really before getting engaged in the project, I was wondering how to do this with the secondary school students, because maybe they don't have enough physics material to do it. But I said we will start. The first step was to ask the participants to make a presentation about communication in general. I asked them for a very short one. So they, 1 or 2 slides, and they did this single slide with talking about briefly about communication with the tam-tam with sound, or with the smoke, with telegraph, string phone, and phones as the original phones, and the new generation of phones. So I asked the students which kind of communication system you can, if I ask you to make experience to show me how those systems work. They said for the first and second one, no problem. They said telegraph, maybe we are not able to do it. The only one they were able to do is this, in addition to the first one. I mean the string phone. And they did it, and they really had a lot of fun doing this string phone. You know, I don't know, we, in my old generation, we used to play with this kind of phones. You need just 2 plastic caps, a wire, and that's it. You have to be distant. The wire has to be, has to be tight. And they explained, as everybody knows, what is sound propagation, and they were really able to understand how does this string phone works, and they really had a lot of fun. Then I told them the second step, we will try to do something more complicated, that is telegraph. So I asked them to read a little bit about telegraph, and they understood that to communicate with telegraph, you need to know this this code. I mean, for example, if I want to say SOS with the telegraph, I had to say S, that is tit tit tit, O, that is tit tit tit, and tit tit tit. So SOS is tit 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 tit. And I told them we can do this with very, very simple circuits. Let's call it LED Optical Telegraph. For this telegraph, we need a transmitter, a receiver, and some electronic material. The material is very, very, very simple. They need a battery, they need on-off button, LED, all in this material. The most expensive part is the battery. All the other parts are very cheap. And as you can see, the circuits is very, very simple. So I gave each of them a set. Each of them, I gave him a set of those parts, and I asked them to make the circuits. It was, of course, I gave them the scheme, the scheme of the circuits. It was really this step of the project was really wonderful step. They really enjoyed the activities, and they fixed the parts only without any soldering, without anything expensive. They just needed a piece of cartoon, like here, and they fixed all the part on the cartoon. When the circuits were working, I have some here circuits. Can you see the circuits? Excuse me.
Yes, ma'am. Yes.
Can you see the LED circuit here?
Yes.
I have
It is visible, ma'am. Now, yes.
Now it's visible. Okay, you can see it. So in this circuit, they just have to, you see, they need cartoon, battery, and the LED. This is the emitter, the button, and that's it. When all of them did this circuit, I asked them to do some soldering. I brought the how to say, the iron, we call it iron, for soldering, and they were able to solder. And this is after many in this project. I worked with the students 1 hour per week, so it took them maybe 2 weeks to be able to do this, to fix properly the paths of the emitter on a cartoon and the paths of the receiver on the cartoon. The emitter so is a LED, and the receiver is a photoresistor. That's it. After this step, they were able to see if they move the receiver and the transmitter one from the other, they lose signal. They will not hear any. So when they put the light on, they hear beep on the sorry. They can hear beep on the. Can I show you the experiment, please?
Yes, ma'am.
So I have to stop.
Stop share. In
Stop
Teams.
share. Wait a moment. I will stop share.
Yes, ma'am.
Okay. I will take the image. Oh, yeah. The circuit, the emitter. Receiver. So this is. So as you can see here, the connection.
You take little higher height, ma'am.
Sorry. Yes, I will do.
A little. Yes. Now it is visible.
Okay.
Yes.
So this is my transmitter. Moment, excuse me. It was working this morning, but when we do things. So you see the transmitter?
Yes.
Other way. Like this and like this. Okay, so here is my transmitter.
It is glowing.
And the receiver is there.
Yeah. Yeah, it is
Then-
visible.
Yeah, but there is a problem, maybe with too many problems today. No, maybe the problem. So anyway, I put the emitter, which is the LED, in front of the receiver, and when I put the light on the receiver, you hear beep, beep, beep. I will use my phone. Sorry.
Hmm. Yes.
This should be the LED. So beep, beep, beep. This is our beep, beep, beep. So you can do like this, your Morse code, okay?
Yes, ma'am.
Now I'll come back to the presentation. Okay, once again. So you are able to see my PowerPoint?
Yes, ma'am.
Okay. And as I told you, if you move the receiver and the transmitter from the other, you will not receive, the signal becomes more and more weak. And they were able to understand. They took an optical fiber here. I gave them an optical fiber, and they were able to see that with the optical fiber, the light travels in the optical fiber, and we can, like this, send signals from transmitter to receiver, which are very far from each other. And the aim, the subject of the project is to send sound, not beep beep. And what I told them was this. This is the system, the communication system we are going to test. We need here to send sound. We are going to use an emitter, a receiver, and a guide between. If the emitter is far from the receiver, we need a guide between, and if this guide will be an optical fiber. And I told them to understand how we can send sound with this emitter. They have to print the sound on a wave, on a light wave, and then convert everything in. Everything will be sent as an electromagnetic wave, that is light, through the fiber optic, and then the receiver will do the necessary, that at the end we will be able to hear sound. But before doing this, I told them they need the preliminary consideration and the reminder. The first preliminary consideration, once again, sorry. Again, the problem of the computer. Excuse me, I will have to restart once again. I'm so sorry. This is the first time it happens. Can I restart? Excuse me.
Yes, ma'am. Otherwise, yes, ma'am. Yes, ma'am.
I'm sorry.
Ma'am, you will do one thing. You send me email of your PPT. I will share from this side.
Maybe. Okay. Thank you.
Yes.
Okay.
Welcome back, ma'am.
Hello.
Yes, ma'am. Hello. You are audible. Your video is also clear.
Okay, let's try once again. I'm so sorry. This is the first time it happens. I don't know what is happening with my computer. Maybe a virus or.
No problem, madam. No problem.
Very sorry. Okay. So you see the PowerPoint now?
Yes, ma'am. Yes.
Okay. As I told you, at this step, they needed some to remind them or to introduce them some preliminary. The first preliminary was about geometrical optics. It is the subject of module 1 and 2. I'm not going to talk about all the modules, but the little small parts of the module. This is very interesting thing, but I will talk about it very quickly. The first, so in this, oh, sorry. In this slide, I show one prediction from module now that is the following one. The participant, this is supposed to be a point source. This is a kind of cylindrical lens or semi-cylindrical container, and the participants are asked to draw the pattern of light with 3 rays, one going to point number 1, point number 2, and point number 3. This is supposed to be a transparent medium. This is the center of the circle. And you can see the prediction here. There are very interesting predictions. These are teachers, inspectors of secondary schools. You see, they are worrying only about what is happening here in this separation between air and the transparent medium. When they, you see, this is their prediction. When they arrive here, the ray stops. Okay. A prediction is always a prediction. We never discuss prediction. Sometimes we ask the participants who agree with this prediction, with this one, and that's it. And then they move to the other step, that is doing the experiment. It's very easy. They use laser. This is the semi-cylindrical lens or water container, it could be, and they can see, in addition to the reflected light there is also a transmitted ray, and then they can do some measurements and go to the Snell-Descartes law. They can also see what happens if the light travels from the material, the transparent medium, to the air, and they can see that in that case there is this is the incidence angle here and here, and they can see that in that case there is a limit angle, and they can measure it for this in that case. After understanding the reflection and refraction Snell laws, they do this very simple experiment that explains how a fiber optic works. And they understand that, you see here, they have a bottle of water filled with water, a hole this side, and here there is a laser beam, and the laser goes to the hole, and then the light is curved inside this water stream. And you can even see some reflection here. So they can understand, we can see here the figure, and they can understand like this, that this could be the fiber optic and how light can travel inside a fiber optic. and they use here the light source, send the light under the optical fiber. The light travels this way and it goes out here. And they can notice here that there is a diverging light at the end of the optical fiber. So since the light is diverging, they will need a lens to converge. So they can learn this is I saw many conferences in many sessions about sophisticated optical fibers. I will not discuss this, but David showed you the first day what this kind of lens does. It makes the light converging to one point. That is the image of this diverging source. We can use this plastic or plexiglass lens is very expensive in my country. I don't know how it is in other countries, but sometimes we go to visit opticians and ask for lenses for glasses. Sometimes they have very cheap, we can find very cheap lenses, and they can give us for free. If they are not using some lenses, they can give them us for free. And you can see with a very simple experiment, here is we have a torch with a slit, with a arrow. This is the lens converging, positive lens, and this is the image of the lens on the screen. The screen is a piece of cartoon. You can hold it by something like this to hold the closest on. And they can remind the ray diagram here. They can understand it more clearly. After understanding what happens with reflection, refraction, and lenses, they have also to understand something about interference and mainly grating, diffraction with dispersion with gratings. Because when the light travel, when you have multiple wavelength signal traveling around an optical fiber, in optical communication, you have to separate the different, let's say, colors or wavelengths, and to separate the signals at the end of the communication system. So this is interference and diffraction is the main goal, main subject of module 3, and they have, from one of the prediction is to predict what happens to, this is supposed to be a laser beam incident on double slit, and they are asked to answer, sketch the light pattern you observe on the screen in the box. So here in the box below, they have to sketch what happens on the screen. And generally, for inactive learning process, we have to show them the material. For this activity, you just need a laser, that is this very cheap semiconductor lasers, and slits. The slits you can do them at home, homemade slits. You just need a piece of mirror. On the coated face of the mirror, you do your best to cut very, very close slits. So here you might see single slit, but it is double. You can hardly see that it is double because the slits are very close. But here in B, here you see, you can see maybe clearly, do you see the double slits here? Hello?
Yes, ma'am, yes.
Okay. So I will give you some prediction, some participants' prediction. You see, here is one prediction who the participant is not worrying about the screen, he's worrying about what is happening between the slits and the screen. While the question asks what happens on the screen. So, I mean, even the teacher do not read, this is done by teachers. Even the teachers do not read clearly carefully the questions. When they are in the workshop, they behave like students, not like teachers. This other prediction is based on optical geometrics, and it's good. If it is optical geometrics, it's good. I say good, not right, but good. I mean, each prediction is very welcome in our workshops. This prediction is based on mathematics. You never see this on a screen. This prediction is made by someone who knows theoretically what happens with he has in mind the image of interference pattern in a particular situation where the laser beam is very large. These are two other predictions which very, very close to the experimental results. You see here that these what we call normally called fringes are not the height of the fringes is not like here, only because this is the size of the laser beam. That's it, the height of these fringes. So you can see that the guy who did this prediction, knows about interference and diffraction, and this is very close to the reality because here are the interference fringes, and this is the modulation because of the single slit diffraction by single slit, which this is the pattern you have with the single slit, this is the pattern you have with double slit. And how to explain to secondary schools students why you have this, you have interference, and why you have this pattern. You can explain first or remind them because they know what are mechanical waves on water surface. So you can come back to water waves. You make a water container here with 4 rulers, a sheet of plastic. Here is the container. You put it on an overhead projector, and you put drop. I will try to go quickly. Sorry, the time is going over. So when you put droplets in the water container, you will see on the screen ripples. They are like this. If you put few drops, if you increase the drops per second, you will see something like this, and you can talk about wavelength and frequency and so on. And if you, here I have a ruler with 2 pins at the end of the ruler, and with this on this container I can make simultaneous ripples, and you can show them what happens what is interference when it comes to water waves. And then we can assume for light wave model oscillating electric and magnetic field perpendicular to one another. This is supposed to be the propagation direction. And we can ask the students, I'm going very quickly, if the same situation than before, this is the picture, incident light, parallel rays from laser. Here are the slits, number 1, number 2, and P is a point of the screen. The question is, do the light waves from slit 1 and slit 2 have the same wavelength from slit 1 and 2? The answer is yes. Are they in phase when they leave, and so on? And then we ask questions about here. What happens? Are the waves, light waves, still in phase when they reach P, and so on? And they can understand very quickly what is in phase waves here, and what are out of phase waves when they come from the wave 1 is the one coming from slit 1 here in P. Wave 2 is one coming from slit 2 here in P. With a very, very simple demonstration, we can show them, we can show to the students or to the participants with this very simple, what happens? I mean, this is a situation where this is supposed to be the 2BP on the screen. And in this situation, we have wave 1 and wave 2 are in phase. And the result on the screen is more intensity than when the here and then this one and this one. Same thing in the center of the interference figure. There you have maximum. In other points of the screen, the waves are out of phase, and in that case, zero intensity. This results in a dark fringe, and this situation results in bright fringes. Okay. We can also make a demonstration with the ribbons for interactive lecture demonstration. And the ribbons, you can make them with ribbons that could be a stick meter or something like this, and put colored tape. This is the dark, this and these are supposed to the positive parts of the wave and the electromagnetic or electric field, and this, the white part, is the negative part. And you can show that here, for example, the waves are in phase when they reach the center of the interference figure. We can also see that when with slit A we have this pattern, and with the slits B we have this kind of pattern. That is when the slits move far from the other, the fringes become closer, and the interfringe, that is distance between consecutive fringes center to center, decrease are smaller with the further slits, and they are here, that is. And if the distance here between the two slits is small, the fringes, the bright fringes, are larger. They can also, if they know the wavelength of the laser, they can measure the interfringe, and knowing the distance between the fringe and the screen and the slits, they can calculate the distance, the small distance between the two slits, the separation of the two slits. Using the model, that one. Using this model with instead of having here two slits, we can put more slits. I mean, more one slit here and one slit here. So one wave coming from here and one wave coming from here, and then but the students or participants can understand that with the grating that is a big number of slits close to one another, instead of, this is what we have with double slits, and this is with grating with few number of slits. You have the bright fringes stay always in the same place, and the dark fringes become larger. You can understand it very easily with the ribbons model. And if you put a big number of slits, many slits per millimeter, the fringes become very bright spots, and they become very far one from another. And you see here the zero order, the first order, and the second order, but intensity is very big. In these activities, you don't need cheap grating. You just need you take your grating from a CD. You see, when you start cutting a piece of CD, the coating starts. You can remove the coating. You have to use a bad quality CD and not very expensive CD. Double-sided doesn't work very well. And you can remove this coating by putting tape on this part, and when you remove the tape, it takes the coating with the tape, and you have the transparent grating. So the slits in this grating are not parallel, they are a little bit curved because the tracks of your CD are circular. So in this almost parallel, in this part of the grating, the slits are almost parallel. This what happened. This is what. So what I show you here is what happens with the red laser. The question is what happens when we have polychromatic laser, that is polychromatic light, that is white light, for example. This is one prediction, and also with this demonstration, students can see that you will be able to separate the colors with grating, and you will have the blue closer to the center, and then red, and the same what happens here on the top same thing, you will have it from the other side. You can make a demonstration also with two colors, and the result will be as I told you, blue closer to the central part of the spectrum, and the red outer. So as I told you, this is not the final version. I cannot open the final version. And to be able to see dispersion, it's good to make this spectroscope, which is made with. I have the spectroscope here in hands. You need any tube, dark tube. It could be the section could be circular or rectangular, it doesn't matter. And from one side of this tube, you put a grating that is here, and on the other side you put a slit. So on this side I have the grating and the slit, and on this you see my spectroscope here.
Yes, ma'am.
Okay, and then when you want to see what happens to the light when using this spectroscope, try to make quickly a demonstration. Okay, so here is the spectroscope. This is the grating side, and this is the slit side. You have to make sure that the slit, this one single slit, is parallel to the slits in the grating. And when you put your eye in here on the grating, you will see what I will show you in. So
it's grating. It's a rainbow.
Let me.
Earlier it was seen, ma'am.
Sorry?
Now it is seen. Rainbow.
You can see? Do you see the light, the white light spectrum? No? You see or not?
Now it is seen. Beautiful, beautiful rainbow. Yes,
You
ma'am.
can see. So this
Yes.
is what you see with your own eyes when you put your eye on the grating side. Okay.
Yes.
And the blue,
Yes.
the central part is white because it's superposition of all colors, and from each part you can see a nice rainbow. Okay.
Yes, ma'am.
Can I take 5 or 10 more minutes to finish the presentation? I'm so sorry for that. Okay, can I?
Yes, ma'am.
Thank you. So this is what we can see with.
Yes, yes. Just now we have seen that.
Okay. This is Alex making fine with the spectroscope, and when generally when I attend the workshop, I give the participants the gratings from CD and ask them to make their own spectroscope, and they are always very happy to do this activity. I think you remember in Alopiu when you were very happy to do your spectroscope. And it's a very nice tool, this spectroscope. I introduced my quantum mechanics course using this spectroscope. And it works well. Now let's come back to our initial project, which is the title is in French here because this is the old version of the presentation. Sorry, and I show here how to the students, of course, how can we convert the sound signal in initial sound signal here to an electromagnetic field. We have to print it on this is a sound signal. This is the wave, the light wave. You just have to print the sound signal on this light wave and send it over this circuit. So the next step of the activity will be for the students making this circuit, making that one, and trying to see what happens. Okay, this is the main difference between this circuit and the optical telegraph is that in this part we we have to take an audio signal coming from a phone or from a computer, print it on light, the LED, and send it to the receiver. So for the participants, we first try the circuits for them. I mean, when the circuit is a little bit difficult, like here, we show them that it works, and we ask them to do by their own circuits, not using those very expensive bread. How do you call them in English? Bread. How do you call them? Bread something, and we ask them to do them on cartoon as they did for the telegraph. Also, we instead of using a signal, single signal, we need to send not only one signal but multiple signal. And so instead of using one LED, we can use 3 colors LED and send a signal for each color, red, green, and blue. And they first of all they have to see what is a 3-color LED. It is here. They mount it on a piece of cartoon, and they have 3 buttons here. They turn first of all the red, the green, and the blue, and when they turn 3 of them together, they see that the color is white. It was very funny for them. And then to do multiplexing, this is in French, they have to do exactly the single LED circuit. I mean, in this multiplexing circuit, there are 3 circuits similar to the previous one. This is the 3-color LED, and they have to mount the 3-color LED like this. for the three-color LED, it is very expensive here in Tunisia. So we also made the circuit for them. I mean, we showed them how to make the circuit, and this circuit is done by students after we showed them the circuit. And here are the circuits done by the students. This is the emitter circuit in two versions of the emitters, one on cartoon, and this is some specific support, not very expensive, very cheap. And this is the receiver. So this is one color emitter, and this is three color emitter. And I will show you how I will show you how does this.
Yes, ma'am.
So I will show you this demonstration.
Yes.
Do you hear the sound of the video, please?
Video, it is visible, ma'am. Sound is not coming, but.
No sound? No? No sound?
Video is going on, sound is not there.
Sorry. Okay, let me explain. We did the test before starting the workshop, you remember, and it worked, right?
Yes.
Oh,
Yes.
I don't know why. So, okay, let me explain you what happens, and please believe what I am telling you. You see, this is the three-color LED. It is here. This is the photoresistor, and this is the receiver circuit. This is the emitter circuit, and this is the how do you call this? And this is the to hear the sound. Okay, we can with this circuit I can put the red color, only the red, the green, what is this? The blue, the green, and the red. Or I put three of them on together. And we put in this demonstration, we put one sound that is song, one kind of song on this channel, and another instrument like lute, for example, or oud on this channel. And here, when I hear only I will hear only one sound because only the green is on. Here I will hear only one sound because only the red is on. And when I put two of them on, I hear two sounds. Okay, so if at the end of the, can you see the PowerPoint now?
Yes, ma'am.
Okay. So when I send signal, when I send three signals about coming from this three-color LED through the optical fiber, at the end of the optical fiber, I will have superposition of three sounds. So it will be noisy, and we have to separate the three sounds as you saw in the conference of this morning. And this is why I was talking about the grating, and we just need to put grating at the end of the optical fiber. I'm not using the optical fiber here, just showing the signal coming from the three colors LED. And also we put a lens because the light coming out from the optical fiber or from the LED is diverging. And this is what we see on the screen here. We can split the three colors. And if you put the photoresistor here on the green, you will hear the sound, only the sound on the green channel. And if you put the photoresistor here on the red, you will hear only the sound coming from the red channel. Okay, I come like this. I come to the end of this presentation. Just want to show you the last slide. No, not that one. Oh, okay, must be at the beginning. It doesn't matter. I wanted to show you some pictures with the group, the team, but it is only in the last version, not in this one. The many pictures of the 4 secondary school students presenting their project to the Optical Society of Physics in Tunisia, to the Tunisian Physics Society. They even presented their project to the French Experimental Physics Olympiad. And they were not the first, but they had congratulations of the jury members. It was a wonderful experience with those students, but also my experience with the active learning workshop and active learning teachers in Tunisia and in Tunisia and all over the world has been a wonderful experience, and I will continue. I will be retired next year, and I have a very nice activity for my retirement. Thank you so much. I'm so sorry for these problems of computer.
No problem, ma'am.
Thank you very much.
Yes, thank you, ma'am. In this online teaching, a few times it happens.
Sorry?
Thank you, ma'am. Now, the session is open for discussion. I request participants, if they have questions, they can raise their hands, or else they can unmute themselves and ask a question to ma'am.
Okay. So I will stop the presentation.
Yes, yes, ma'am. You stop sharing, ma'am.
Okay. Is that okay now?
Not stopped yet.
Huh? Not yet?
Not stopped. You just one more time. Keep.
Okay. Now it's okay.
Yes, ma'am.
I wanted to show you many experiments, but sorry,
Yeah.
we lost a lot of time, and
Yes.
Yeah.
No problem.
Just to show you, you use very inexpensive torches. The slits are there. You use this kind of clips to fix the screen, the layer to keep the laser on, and so on. But okay.
And clay to fix the components.
And clay to fix the components and so on. I really love the activities. I wanted to show you the strings here for interference made on meters. You see?
Very nice.
Yeah. What I wanted to say is that it's really interesting. You understand many things when you prepare this material. And also you have to be volunteer, you have to give your time, you have to love physics, otherwise it doesn't work.
Yes, ma'am, sure, ma'am.
Okay.
Yes.
So please, questions?
Dear participants, if you have questions, you can unmute yourselves, else you can raise your hands.
Excuse my English, it was...
No problem, ma'am. It was perfect.
While waiting for questions, I will show you some. I told you that this semi-cylindrical plexiglass is a little bit expensive. This is a semi-cylindrical container made by participants. It is
acrylic.
It's acrylic. This is supposed to be. It was a box for. What do you call this? I don't know. For they cut it. They cut it and they closed it by a piece of plastic here, and it works for the activities. It works very well.
Yes. Very nice. Dr. Parthi Patil, ma'am, please ask your question. Unmute
Good
yourself.
evening, ma'am.
Good
Good
morning.
evening, ma'am.
Good evening.
Good
Sorry.
evening. Oh, good morning, ma'am.
We don't have the same time.
Love your lecture a lot because you have taught everything with the help of experiments and with active involvement of students. It is a nice session for us so that besides telling only theory, one can incorporate such type of experiments which are inexpensive and students can easily do them and enjoy physics learning. Thanks a lot, ma'am, for giving us such type of beautiful session. And my question is that while delivering lecture, you are conducting such type of sessions, or you are allotting separate hours to do experiments. Means in laboratory you are doing, or in class you are doing such type of activities.
Look, interactive lecture demonstration or even the other activities, I mean, hands-on activities could be done everywhere you are. You know,
Okay.
even in the garden of the university, or you can do them without any problem. I was not able to show you some pictures because it is in the version I lost, but I have pictures of me and students carrying bags with the material, moving to the university or moving to the school, or you can do them. Once one of my students told me, Madam, even my grandmother, he made his spectroscope and he was looking to several light sources at home.
Okay.
He did it at home. And he told me, even my grandmother was able to see spectrum and to thanks to you.
Yes.
So you
Oh.
can do them everywhere. It takes
Yes,
time.
yes.
I mean, when you teach, you cannot do every day, every session active learning.
Like this. Okay.
Students interested in experiment and in doing something with hands. That's it.
Yes, yes. Yes, ma'am. Thank you very much, ma'am. Thank you.
Thank you.
Thank you.
And if you need, you want to duplicate experiments or you did any assistance, please, you can have my email address and ask.
Okay,
I will
ma'am.
help with great pleasure.
Okay, okay. Thank you very much, ma'am. Please share your email ID with Abhijit sir so that we can
I have
take.
email ID, I will share with them.
Thank you, sir. Thank you, ma'am. Thank you.
Thank you. Thank you. Welcome.
Thank you.
Another question?
Any other question?
Maybe the time is over.
Yes, yes, yes. If there are no questions, I request one of my colleague, Professor Mallikarjun Bisesar, to propose vote of thanks.
Thank you.
Thank you.
And
Thank you.
sorry.
Thank you, sir. Very good morning, madam, and good afternoon, one and all. It is my privilege to have been asked to propose the vote of thanks on this occasion. I, on the behalf of the Department of Physics, Electronics, and Photonics, and Rajarshi Shahu Mahavidyalaya, Latur, and my own behalf, extend my sincere gratitude towards Dr. Souad Lahmar, madam. During the session, madam has focused on how to teach optics in an active way, which will help us to increase the interest of the students in learning optics and encouraging students to join the research in the area of optics and lasers. During the session, madam have also discussed about students should be allowed to make prediction before doing the experiments as a part of an active learning. The experiments on the data transmission using the LED and the photoresistor were very interesting, madam. Madam, thank you for such an activity-based, informative, and interesting lecture. I would also like to thank Dr. David Sokolov, sir, for giving his valuable time to us, and thank you, sir, for joining us. I am also thankful all the participants for their active participation. Thank you very much. Thank you, one and all. Thank you, madam.
Thank you so much. Thank you. It was my great pleasure to participate. And once again, sorry for all the problems we had.
No, ma'am, it
Thank
was a
you.
wonderful session, wonderful interactive, illustrative session. We are very much thankful, ma'am.
Thank you. Thank you very much.
Thank you.
Thank you. Bye.
Bye.